which is very good. And another thing we noticed was these are Kagoshima University film that has probably less pure than SGI film, and they have a TC of about 31 Kelvin, and then they have we got two films, and then measured these, and then as you can see, there is a thickness effect. The SGI film is the thinnest one, and then Kagoshima University number one is the second thinner, this one, and then the thickest one is the lowest. So you can see this thickness effect as well. Okay, let me come to this other definitions of H field, where we took two other field, H star and H derivative. H star is the field where it goes the bottom of this curve, and then H derivative is derivative of dmdh, and then when it starts to kink, that's where H derivative is, and both H star is clearly above vortex entrance, and it's above HC1, of course, and H derivative is very similar to this, and then this means this indicates the sudden entrance of large number of vortices, and this is quite relevant to our cavity field, or cavity, I guess, I hope. Okay, so this is from same company, STI. The thickness effect was, this is a H derivative field, and thickness was 300 nanometer as temperature versus the derivative field. And we measured a 500 nanometer film, then this came this one. And then it's interesting to see from the two fluid model, this curve is quite different. That suggests that there's thickness effect already happening here. If it's two fluid model, it goes like this. So one of our Los Alamos researchers is writing a paper on this, explaining this. Okay, so HC1 measurement or H derivative measurements have shown that even the thickness of the MGB2 is, even if it's thicker than the penetration depth. Penetration depth is probably like 100 or to 150 nanometer, and then we measured like 300 nanometer film, but it's still, as you can see, it increased a lot. So it was very interesting and encouraging for us. However, as I will show you about RF measurements results, okay. I can skip this because Sami explained to you. This is a SLAC testing setup with the hemispherical cavity, and the sample is here. And then when it quenches, this circular area starts to quench first. And we measured the Q and quench field. Okay, before going to the quench field or critical field, this is a measurement of the Q versus temperature at low field with various samples. At first, we made various types of MGB2 and boron. The reason why we called it boron was just easy from the system, and we hoped that would be able to sort of disconnect the film, the MGB2 by boron. And so the first result was like this. There are two transitions. For some reason, for this measurement, the TC was about 2 Kelvin lower. I don't know why right now. It was about 37 Kelvin compared to the DC measurement that showed 39 Kelvin. And also, before measuring this MGB2 film only on sapphire, we didn't really calculate about this resistance, surface resistance of niobium, but it turned out it's very high, a few, like 2 or 3 orders of magnitude high, and as Sami said, it was partially due to the ambient magnetic field or external magnetic field within shield, but still, I still don't understand that it doesn't really go to this from what I saw from Sami's data. But anyway, so there are two gaps with those two MGB2 and B layers. And after all this, we did this MGB2 only 300 nanometer on sapphire, and then we saw really high Q and dominated by the host cavity, and this doesn't tell you what's the surface magnetic surface resistance actually is, because it's dominated by the host cavity. So to really know what exactly the surface resistance of this film, you have to have a like all niobium cavity, for example. That's why Sami said we want to make a host cavity made of niobium. And also, I'm hoping that we can measure more exact number or accurate number surface resistance at somewhere else, like Jefferson Lab. Okay, so this just tells you that even interesting thing about this is even with magnetic field, this MGB2 was very high. That's one of the interesting things. Okay, let me come to this the surface peak field versus Q data. This, as I said, the Q is limited by the dominated by the host cavity, copper, and then it was very straight up to about 25 millitesla or 250 Elsted, and then all of a sudden it quenched. It looks like it's not a heating effect, but I'm not actually sure, because you don't see very accurate surface resistance difference because it's dominated by the host cavity. If this is true magnetic critical field, it only shows about 25 millitesla or 250 Elsted, which is very low compared to the DC measurements. At even 4.5K, it was 200 millitesla. So I'm puzzled. But I'm a little bit encouraged by that Shaoxin's RF data that showed high number. So this it might not be true critical magnetic field with thin film. Okay, let me move on to issues and concerns. When we code MGB2 with B boron on bulk niobium, we had this issue of oxygen and magnesium at the interface, intermixing of these elements. And also magnesium goes through the boron layer and then accumulated here. It's so this was an issue, and this is still an issue. But we found some way to partially solve it. One way was to let's see. So this interdiffusion problem. One way was baking. Those films that I've shown the result were not baked, and it seems that a lot of oxygen was inside the niobium. And when we baked the substrate at 800 C for 4 hours, it has significantly reduced the oxygen level that comes out from the niobium. And also, we coated alumina before coating MgB2. That was very thick, 300 nanometer. But anyway, and this result was quite similar to what we got without niobium, only sapphire. That was very good. That means this alumina layer can disconnect this intermixing, niobium and MgB2. So alumina layer is a good layer to put between as a dielectric layer between MgB2 and niobium. But of course, we need to optimize the thickness of alumina, and we're working on very thin alumina layer now. Okay, let me summarize. So, as I said, DC measurements have shown the HC1 of higher than 200 millitesla at 4.5 Kelvin. We will test it at lower temperature to see if it goes up. And also, but as I said, RF measurements so far, just 1 or 2 measurements so far have been done, but only about 25 millitesla, 3 Kelvin. And as I said, I'm puzzled. We need more measurements, and we need to know why it's so low. And it might not be true, and this might not be true. But we're more confident about DC measurements because we've done a lot, and we're confident about this. So now what we're doing is we've completed this 3 2-inch samples of 4 layers of MgB2 50 nanometer and aluminum oxide, ALD alumina 10 nanometer, 4 layers of these on sapphire. Argonne National Lab helped us a lot on this, and we send samples back and forth many times, and it's been done. So we're about to start measuring the DC measurement, and also we're going to send these samples to SLAC for RF measurement, and we'll see what happens. And also we need to develop a technique to coat cavity, and Xiaoxin gave you some examples and what he plans to do, and that's next thing we need to do. Okay, that's all I have. Thanks.